All right, so we're taking a quick look at an example of Widrow-Hoff. And so just to remember what that is, we have the Widrow-Hoff 1 is here. I'm going to put this online. And what's coming in is an X and a T. Those are that's the data. And then the learning rate, and then the number of iterations or the number of passes that you want to take through the data. Okay, so now the way I've got it set up, I'm working with dimension by number of points, but you should uh, make sure that that is true in the algorithm that you're working with, because I think Python, some of the other built-in functions work the other way. So be sure and read the instructions before you actually use it. But we're going to use dimension by number of points. And so then we're just going to plug things in. You can see here we initialize W and B, weights and biases. In this case it's 0, but you could do it randomly instead. Then the number of passes through the data. And in this case we're going to go through the data as it's presented, because I want to pretend in this next example that our data is actually coming in one data point at a time, and so that's why I'm not reordering it. If I was to do this as a bulk or a batch training, I would probably reorder the data points so that they're not coming in all at once. Okay, and so then we're going to let's see, figure out what the error is for this data point. That's what you see there, target minus output. And then what you see here is the learning rate times the error times the x. So that is the Widrow-Hoff step, which is an approximation to stochastic gradient descent, right? And so then I just take w plus dw, and then I take my bias is bias plus learning rate times e. Good. And then I'm just keeping track of the error as I go along. All right, so let's try this with an example. And the example I want to look at is the following. I've got some data here. I think it's in signal plot. Signal. Yeah, so this is the data that we want to take a look at. And the reason I'm taking a look at this is you might notice that the signal changes over time. The signal changes over time, and this is the kind of the feature of an adaptive or adaptable. Geez, I can't talk tonight. This is an adaptive linear network. Another way to call that is Adeline. Adeline is short for adaptive linear network. So this is an Adeline, and the nice feature about this is that it's not assuming that the data is always constant. So it's adapting live as you go, as you train. Okay, and so this is my data that I'm plugging in. Now the problem with this is that this is called a time series, and the problem with the time series is I need to try to work out how my function is going to operate on the time series. And so in this case we're going to use the previous, let's see how many values, 5. I'm going to use 5 values of the time series to predict the 6th value, right? And so you might want to read the notes about that. That's called lagging the vector. So I'm going to put this time series into R5 by taking the first 5 points as the first column, the next 5 points as the second column, the next 5 points as the next column, and so on. Okay, and so when I do that, I end up with this matrix X that's 5 by 236. And so I'm going to go in here, and you know what? Instead of showing you what the time or what the learning rate ought to be, let's see if we can take a little movie. And my learning rates I'm going to change from 0.01 to 0.8, and that'll be 40 linearly or equally spaced points between 0.01 and 0.8, and I want to see how the learning rate affects my modeling or the error. Okay, and so now we're going to run through a little bit of a loop to see what happens. That's the alpha j, right? So that's Widrow-Hoff. And now we need to plot the error after we get our W and our B. Plot error. And now this is how you make a movie. You take MJ, oops, not square brackets, but regular parentheses, equals get frame. I'm going to pause this while we're going here so you can actually see what's happening, and then we'll end it. All right, so there's the first error. So this is the error plot, and what you see is that the error didn't really settle down in the first 150 or so points, right? And then when I shifted my time series, you see the error spike, but then it starts to go down again. Okay, so when I'm looking at this, I'm thinking to myself, this error is too big, or this alpha maybe isn't the right alpha that I need. Okay, so let's see what happens next. Okay, now our error is starting to decrease as I increase my alpha from 0.1. Decreasing, 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 decreasing. Is it always going to be decreasing? Uh-oh, oh no. It's starting to increase again. Uh-oh. That's a bummer. And in fact, be careful, because if you start choosing an alpha that is way too big for your data, do you see what's happening? This is called an explosion. Your error is going to blow up on you. And so if you get a plot like this, that means your learning rate is way off. And so you need to cut it way back. Okay, so if you get a huge error like this, notice what's happening here. This is 10 to the 17th power. So we're going to overflow the 10 to the 20. Oh, how big can my error be? 10 to the 34th power? 10 to the 38th power? 43 power? 40? Oh my gosh. I didn't think the error would go to the 10 to the 47th power. Okay, so this is basically infinity. And so yes, we see two things here now that I wanted to emphasize. Number one is that if you find a good error, so a good, not good error, but a good alpha. Let me go ahead and redo this now with a nice alpha. And the nice alpha that I found was 0.153 approximately. Okay, and now if I plot the error, I get a reasonable plot. Good. And that looks nice. And it looks like the error is just about 0. So let me check that. Let me go ahead and say, like, let's see, the output for my network is going to be W times X plus B, right? So let's go ahead and plot that. And now let's plot T minus the output. So that's the error, but not absolute value, right? Oh, what's going on here? This looks terrible. Why is this error looking like this? Oh gosh, maybe I should plot the output instead. Let's see, I think I've done this before. Whoops. What length do I need? 236, I guess, huh? I guess I didn't redo that. Okay, so now I'm plotting T versus my output. Okay. Let me make that a little more visible for you. And let's see what's going on here. Okay, so the black diamonds are the original data. Why does it look like this? Oh my gosh, it looks like the signal was terrible in the beginning. Do you have an answer for me? Anybody know why we're looking at this like this? Was it a terrible output? No! What we did was we used the W that has been adapted for the second part of the network, and we tried to apply it to the first part of the network. Okay, so you'll notice that the error is 0 here, right? And that's because the W has adapted. The weights and the biases have adapted to this part of the network. And so they're going to be a terrible fit to the beginning. Okay, so if I wanted to know what the weights were over here, I would have to record those weights right at the end of our training at about 150 points. Okay, good. Okay, so if you do run into questions like this, let me know, because sometimes it's hard to know what's happening. So Widrow-Hoff, this network training is excellent when your data is not stationary. If your data is moving around, you can use an adaptive network to follow your data around. I'm kind of reminded by some of the guidance systems for like missiles and things. Um, those are actually adaptive systems, and so they adapt to whatever things are happening around them. And this is the kind of thing that you're going to be seeing in that kind of a system. Is you're going to be trying to always decrease your error, and you're always modifying your weights and your biases all the time. You're not just training once and then leaving it. You're always training. Good. Okay, so that was a neat example. I'll stop here and we might take a look at another one.